Alright everyone, welcome back. We're gonna do some more helicopter aerodynamics. My name is Caben Hansen, here with the Flight Zone. Let's jump right in. This is part 3. Alright, cool. Gyroscopic Precession. So, I'm actually just gonna read this. The spinning main rotor of a helicopter acts like a gyroscope and has gyroscopic properties, one of them being precession. This precession is the action of the rotor blade's input occurring approximately 90 degrees later. For example, if a pilot pushes the cyclic forward, wanting to tilt the rotor disc forward, the disc would actually want to tilt to the left significantly. This doesn't happen though, because engineers and mechanics have designed the helicopter controls and linkages more often than not using something called pitch horns to compensate for this phenomenon. So in this picture right here, this is actually an R22. You got the teeter hinge, upper lower swash plate boot. You got your pitch boots. So right here, here's our pitch link. So when we pull the collective up, this lower swash plate, this one spins, this upper one doesn't. This lower swash plate will move upward, pushing the pitch link up, which pushes the pitch horn, which then pushes the blade. And the blade and the horn are offset 90 degrees. So that alone is enough to cancel out the gyroscopic precession, which is pretty freaking sweet, because that'd be weird having to fly forward with the cyclic to the right, you know what I mean? That'd be a little strange and probably pretty irritating. So, gyroscopic precession. Dissymmetry of lift. Once again, I'm going to read this. As a helicopter is in forward flight, the airspeed over the main rotor blades is constantly changing. The advancing blade sees higher airspeed in forward flight, and the retreating blade sees lower airspeed. For example, if a helicopter is traveling at, say, 70 knots and the blades are spinning at 200 knots, these aren't accurate numbers. I'm just putting them. The advancing blades would actually be moving at 270, because we're moving forward at 70 knots airspeed, and if the advancing blade, or if the blades are spinning at 200 knots, the advancing blade would see 200 plus 70. So, in turn, with the retreating blade, we're going to take our 200 knots, but because it's retreating now, we've got minus 70. I might have kind of butchered that a little bit, but it's still the same concept. It would be moving at 130 knots. That might not be accurate, but once again, it gets the point across. This difference in airspeed causes the right side of the helicopter to want to lift more, because there's way more airflow on that side. That would be our right side. The blade is coming forward in our counterclockwise system that we've talked about a few times. So yeah, it'd be lifting more than the left. However, thanks to blade flapping, the leftward roll of the helicopter at airspeed is hardly noticeable. So, flapping, I know the blades, they're going to want to, the right blade, or the advancing blade over here, it's going to want to tilt upward, which it does. They flap, so it's not rigid. It's not a rigid system. The helicopter's not going to roll to the left. The right blade is just going to come up some, while the left one goes down. So, yeah, see, here we go. Forward flight at 100 knots. So let's go over our retreating side. We see our blade rotation here. It's going counterclockwise like an R22. On the retreating side, our relative wind, it's still going back because we're flying forward. The blade tip speed minus the helicopter speed. So we're flying at 100 knots. The blade tip speed must be about 400 knots in this, because 400 minus our 100 forward speed would make 300. Now if we go on the flip side, go to our advancing side, these blades are going forward. So forward flight at 100 knots, and if the blades are spinning at 400, then boom, they're actually going 500. So this difference gets a lot greater as you increase forward airspeed. So it's something that's very important to be cognizant of, be aware of. Retreating blade stall. This goes hand in hand with dissymmetry of lift. And it's actually the limiting factor in a helicopter's top speed, probably 90% of the time. So, retreating blade stall. Using the concept of dissymmetry of lift, if a helicopter is flying too fast, the retreating blade can actually see relative winds so slow that the blade will in fact stall. The angle of attack is going to be too great, generating no lift, while the advancing blade is generating lots of lift, tilting the teeter hinge so far that it has tilting the teeter hinge so far that a hazardous condition could result. I don't think I've really ever heard of this happening, but that's why the V and E speed, the never exceed speed, I've written it down here. Don't go fast. Don't go faster than the manufacturer of the helicopter has said not to. Like I think on the R-22s, the V and E is 102 knots. Don't exceed it. The concept of retreating blade stall is usually the limiting factor of the top speed of most helicopters. Blade stall can be avoided by staying below the helicopter's never exceed speed. And I think, yeah, it's basically the same thing, but with higher speed. Alright. This is going to be a pretty short video, by the way. Because I'm mostly reading it and then explaining it, it's kind of helped me overcome a little bit of stuff too. So, let's keep it going. Effective translational lift. There's also translational lift, so we'll talk about that in a second too. As a helicopter is pushed into forward flight, the rotor blades become more efficient as induced flow is decreased and more forward air is coming into the rotor disc. So, induced flow, that creates downwash, remember? So, we're getting out of those vortices that we're creating. Like, they're still causing drag. Don't get that mixed up. That'll always be there. But that downwash that we're kind of generating, it's getting behind us. So that's a good thing for efficiency. Think of it as moving into the air as opposed to pulling the air into the blades. So yeah, as you're moving forward, the helicopter is flying into air instead of hovering, where it's pulling air into the top. Induced flow, basically, you know? We kind of went over that in the last video, I think. So, the induced flow is decreased. The helicopter's outrunning some of the vortices it's generating. So, that's translational lift. Basically, that is the kind of outrunning some of them. As the helicopter accelerates above 16 to 24 knots, that can vary. Like with the R-22, I think it's like 10 to 20. Anyway, as the helicopter accelerates, most, if not all, vortices are being outrun. And the helicopter is now at its most efficient state, which would be effective translational lift. That's when you're outrunning all vortices. You're outrunning all of the induced flow. So, pretty sweet. Very efficient. The most efficient a helicopter can be is when it's light, when you are you have the least amount of drag possible, which we talked about. There are 3 different types of drag, and that's in video number 1, part 1. And of course, when we're in effective translational lift. Very cool. Here, let's actually go back. Here's a picture. So, this is kind of a decent, it's a good representation. So, you see these kind of vortices here towards the back. So, the helicopter is kind of outrunning them. Like, they're not being pushed straight down. They're not coming back up into the rotor disc, you know? So, that's kind of the general idea of translational lift. And then effective translational lift is once you start getting more and more speed, The whole rotor disc almost acts like a wing, sort of, but not really. I'm not going to confuse y'all with that. Transverse flow effects. So, this one also has a 90-degree rule. So, not to get confused with gyroscopic precession, transverse flow effect is the aerodynamic force that's generated by the main rotor blade that occurs 90 degrees later. So, gyroscopic precession is the mechanical, physical force that makes the main rotor want to tilt 90 degrees later. So, let's not get that mixed up. That took me a while in flight school to actually understand, because I thought transverse flow effect and gyroscopic precession were actually the same thing. They are not. One is mechanical, one is aeronautical, like it's an aerodynamic force. So gyroscope is mechanical, transverse flow is strictly air. It's kind of like a phenomenon. So transverse flow effect is most noticeable during transition from a hover to forward flight. The extra air being introduced at the front of the rotor disc as the helicopter moves forward actually creates lift 90 degrees later, which will push the left side of the helicopter up, causing a slight right roll. The pilot must anticipate and correct this during acceleration to stay straight. So it's a pretty simple concept. As the here we go. This is the front of the helicopter. As it's moving forward, more lift starts getting generated towards the front because more air is coming in up there. Well, that lift actually gets generated 90 degrees later. So that blade is going to go up, less lift here, which is pushed over here. Blade over here is displaced down. So it's kind of the opposite. Transverse flow effect is the opposite. It is your retreating blade that's going to want to come up because the front, this is where the lift is generating, and it's coming into effect over here. So it's pushing this blade up. It'll make the helicopter want to roll right, so when you're moving into forward airspeed, put a little bit of left cyclic in there to keep it straight. Nothing to really worry about too much. Alright, sweet. Autorotations. Autorotations are something else. This is what prevents us from falling out of the sky if the engine goes out, thanks to a sprag clutch and some aerodynamics. An autorotation is an aerodynamic display that the pilot must enact in the event of an engine failure. As the engine is no longer turning the blades, the upward flow of the air through the rotor disc is now the only way to keep the blades spinning as the helicopter descends to the ground. To perform this as safely as possible, the pilot must lower the collective to reduce blade pitch in order to keep the rotor RPM up, and apply some right cyclic to counteract. I meant to put right pedal there. Apply right pedal to ignore that I said cyclic. Apply some right pedal to counteract the sudden loss of torque from the engine. The cyclic and collective will be used to maintain proper airspeed and rotor RPM. So this right here is a pretty decent example. So in normal powered flight, the helicopter is pulling itself through the air with powered rotor blades. Oh no, the engine went out. So put that collective down, put some right pedal in there so that we stay straight, and pull a little aft on the cyclic to not fully level ourselves, but to, lose our nose down pitch. We're going to sort of not fully level, but a little level, still keep the nose forward some. And so now the air is moving up because the direction of flight here, we're flying downward because our engine's out, we're coming down. But we're going to control that collective and that cyclic to keep our speed and rotor RPM in an acceptable spot. So there's another slide to this. Upon nearing the ground, the pilot must flare the helicopter, lowering the collective and pulling aft on the cyclic. where the helicopter will then stay suspended above the ground for a short time, bleeding off its RPM. With the inertia that remains in the rotor disc, the pilot will level the aircraft and pull up on the collective to cushion their landing on the ground. So here is an example right here. We've got an R-22. He's over the runway. He's got some forward airspeed. All right, looks like he cut the throttle.
Autorotation flare onto.
A limousine stop is when you're on the brake.
So here's an example here. There's an R-44. There's his flare. Collective down. And he sort of cushioned it. He still had some forward airspeed there, but that's okay. You probably heard there the engine was still in fact running. For training purposes, you're not going to actually turn off the engine during an auto rotation. That's just for safety. But in the real deal, you're not going to have an engine. So, yeah. Alright guys, try to keep it a little short, try to move and sort of get that information out there. Made it to where I could read it, try not to stutter so much. But thanks for watching, hope you learned something. You can find a lot of this stuff just on the internet. I'm kind of referencing the Helicopter Flying Handbook, a lot of this. And yeah, if y'all have any questions, leave a comment, leave a like, subscribe, and I'll see you on the next one. Fly safe.